Welcome to the first of the talks on atomics and log-free and all the concurrent stuff. That there will be several more, and I'll try to introduce some of the materials that will be covered later. This is in two parts. We'll find a good place to break. So the roadmap, well, we'll get through all the stages. Yes, I will do the double-check-locking. Everybody does it. I have my own twist on it, so I hope I can show you something interesting, even though the subject has been beaten quite to death. No, this was... On Wednesday, I give a talk about handling exceptions. This was supposed to happen then, not now. Okay, this one is not about handling exceptions, so wait for exceptions for Wednesday. This is about writing good concurrent programs, specifically with C++. Emphasis is on practical, which means and practical applications, not library development. Okay, how many people here write like applications, you know, the specific, concrete? Very good. Who writes libraries? Well, you may find something useful in this, but you will be limited. Now, I do like questions. I didn't expect to be in this room. I mean, here it's hard to pass mic, so if you can project and something is unclear to you, try to interrupt me and ask questions. I don't like to leave anything unclear as we go through, because we have 2 hours of material. If something is unclear, by the time we get to the end of even the first hour, you will be missing a big chunk. Also, while I try to be accurate, I am explicitly not going to be precise. I will be jumping over things, I will be simplifying things, and there are several talks following on. If you want to know the real truth, if you can handle the truth, you go there and you learn all about some of the details. The reason I put this on is not, the regular slide about the authors, how many papers, how many of this, how many of that. It gives you the better understanding of, my perspective. Sort of, everybody has a keyhole, everybody has a lens. They look at software. This is mine. I work on software that deals with very large scale problems. We have thousands of cores, hundreds or maybe hundreds of thousands of cores running sometimes for hours, sometimes for days, billions of objects at the same time, and they're getting turned around. If you have 1 gigabyte of memory, we probably have churned around 1 terabyte per hour or more. We write software for sale. We have to write it for whatever our customers running on. How many people write software for sale to external? Basically, your customers, you live by the money that they pay you. Okay, so you understand. We have customers who are very conservative, and the reason they're very conservative is, not because they're stupid or anal, but because if we screw up the production line on a fab, it could really be hundreds of millions per day. Half of our customers are on Red Hat 5 right now. The newest compiler you can get on a standard Red Hat 5 is GCC 3.4 something or other. Which brings us to the subject. Writing log-free programs. Writing log-free programs is hard. What's harder than writing log-free programs? Writing correct log-free programs. In practice, so you go to theory about log-free and they tell you everything about all the problems with logs and all the reasons to go log-free, and you go out and you forget it and you start writing log-free code because you think it's faster. That's 90% fluff. Okay, if you're after the best performance, what's rule number 1 about performance? Who knows the rule number 1 of performance? Yes. or the other way is never guess about performance. You will be surprised pretty much every time. Log-free algorithms, surprisingly enough, do not always provide better performance, even when they are correct. Incorrect ones often provide better performance, though. So I have these take-home points that I'm going to kind of accumulate throughout the talk. If you leave this room and you remember at least one of them, I have done my job well. Now, speaking of doing my job well, who knows what a queue is? Queue. OK, very good. I'll ask the same question at the end of the talk, at the end of second hour. If at least one of you hesitates to raise your hand, I have done my job really well. Since I brought up the question of C++11, C++11 has atomic support and has memory barrier support. As I said, for some people like myself, it's not yet available, not because we can't port our code to C++11 compilers, but because like large portion of our customer base works on systems where these compilers would be a custom software, would require a custom library load, and nothing custom gets loaded on those machines. It's in some way more complex than the simplified level I'm going to be talking about. Now, don't be alarmed if you're using C++11. I will use a kind of pseudocode that you could map one-to-one to C++11. You could implement your own C++ library to that exact interface that I will be using. You can map it one-to-one to boost atomics and pretty much any library that provides memory barriers and log-free atomic primitives. So if that's the only thing that stops you from using it, this is the least of your worries. OK, time for acknowledging the great ones. So last year, Herb Sutter was giving the talk on log-free. And this is the slide from his talk. He was giving this analogy. This is your single-threaded program at the top. Do we have the... Not that you need this right now, but I guess... Well, I'm not so much interested in that. I'm interested in the... OK, we do. And we... Where? Oh, all right. Because I can see it on my hand, but I guess that screen is not. OK, so anyway, single-threaded program, very easy. The traffic lights are like logs, and the highway overpass is like your log-free program. Everything just flows smoothly at high speed. Nobody waits for anybody. This is why it's much better. Since I'm talking about practical, I will do everything is example-driven. So I'll do by example, and we'll try to generalize the examples. This is one of the simplest examples of log-free programming, DoubleCheckLocking. Everybody knows about it. Everybody has seen it at least once. It does have some twists that I like to expose that maybe you haven't seen before. Now, before C++11, it was actually really important for you to know, because there was a huge caveat that you'll see in a moment. In C++11, they made the thread-safe static initializer, which made double-check-locking irrelevant. Actually, no. It made one application of double-check-locking irrelevant. You'll see more. Double-check-locking is actually very useful for practical log-free programming. Toward the end, you'll see why. Well, let's do the classic application of double-check-locking. The classic application of double-check-locking is Singleton initialization. We have some magic gizmo thingy, which has a transmogrify method, and that method is thread-safe. In order to operate the magic thingy, we need to create one, and there is only one of them. There is only one for the entire program. And then we need to transmogrify it. Transmogrify is thread-safe, even if you call it by multiple threads at the same time on the same object. So the question of thread safety is that line with a static initializer. Is it thread-safe? And what do I mean by thread-safe? By design, there should be only one of these objects in the entire program. Well, that's what static normally says. Now, unless multiple threads enter operate function at the same time, then it's a little less clear. C++ before C++11, C++ standard had exactly this to say on the subject. What threads? C++11 introduced the concept of threads in the memory model, so they could now actually talk about it, and they said, yes, it is thread safe. And the compilers said, oh, okay, kinda. Like the modern compilers actually mostly get it right. GCC got it right after 4.04, I think. 4.4, not 4.04. They had a bug where it wasn't safe. Anyway, it's still instructive to go through. So what's the problem? First step, you understand why wouldn't it be thread safe. What does static initialization really do? What's behind that first line, that first statement? Well, we have a pointer which starts its life as null, and let's say it's linker initialized, so it's initially null. If that point, we go through that context of code. If the pointer is currently null, we need to create new object, store its address in the pointer. Otherwise, we don't need to do anything. Well, here is the problem. The problem is we have a data race. Two threads come in, both start executing this code, they both see null, they both go and construct a copy of an object. Now one of them leaks, because you only have one pointer, the other assignment got stomped on. Unprotected static initialization is not thread safe, and what's the root of the problem? The root of the problem is that the checking for null and handling the null, as creating new object, assigning the pointer, the address to the pointer, has to be done atomically in a single transaction. The whole thing has to be done as one uninterruptible atomic operation. This concept of atomic operations, and I don't mean in the sense of hardware atomics, I mean in the sense of this whole operation either happened or didn't happen, but it cannot half happen. Nothing else can go on while this uninterruptible atomic transaction is being processed. So the concept of such atomic operations is central to all concurrent programming, whether you use locks or not. You have to start thinking in these terms. Okay, so the usual way of dealing with that is, of course, if you need an atomic operation, you put a lock around the whole section of code that you want to be atomic and non-interactable. So we put a lock before check for pointer, and we unlock after. This works. There is, however, a big waste going on here. After the few threads go through this, maybe the few threads come in at the same time and they struggle for the locks and so on, but eventually it'll get initialized. After that, it'll always be non-null, and it'll always be initialized, and nobody needs to create a new one. However, we're always taking the lock, locking and unlocking every time. So that's the big waste. Our program has run for an hour, we're still locking and unlocking. Okay. We can, since we know that eventually the pointer will be non-null, we'll just check for the pointer. If it's null, we know that this could be a data race here. So now we're going to take a lock, check again, and this is atomic transaction inside the lock. This is why it's called DoubleCheckLocking. There's only one problem. This doesn't work. It may work on your compiler. I'm told, I don't personally know, that some versions of Visual Studio detect this in the source code as a pattern and emit correct code. If you reorder a couple statements, they don't detect it as a pattern. So what does the initialization really do? Well, it does something like this. First, it has to allocate memory. Obviously, nothing can go on before we allocated memory. Then it has to construct the object in that memory, so that's a placement new. And finally, it has to initialize that static pointer with the address of the temporary memory that we just allocated. That's the three things that must happen. Well, this is also a valid implementation. Allocate memory, store the address of that memory in the pointer, It right now doesn't point to an object yet. It points to uninitialized memory. Then construct the object in that memory, and now you're back to the exact same state. We changed the order. We first initialized the static pointer, then we constructed the object. Both are valid from the point of view of the C++ compiler, which means that the compiler can implement this expression any way it wants. Both options are valid. This one doesn't work for us because the pointer will be non-null. Other threads will go through, see the pointer as non-null, and try to use the memory when the object hasn't been constructed yet. This is a bad ordering. We want to force the other one. Okay. So we're going to force this order. We're going to write it explicitly like this. Allocate first, construct second, initialize third. Optimizers do this. That's what the compiler writer is getting paid for, to detect those temporary variables and eliminate them. So compiler probably reduces it to something like that. Just eliminate the temporary, store the address of malloc right in the pointer, and then call the constructor on that memory. Compiler wins this round, but never underestimate the ingenuity of the programmers. We have a big hammer in C++, and by God, we're going to use it. The problem was that compiler reordered memory accesses. We have this volatile thing, which tells the compiler, do not eliminate any reads or writes and do not reorder them. This is exactly what we need. Well, we're going through this volatile on every invocation, so there may be some performance penalty, but never mind that. Now, compiler cannot reorder. Really, every read and write has to happen exactly in the order that I have written. So allocation has to happen, then the address of the allocation stores in the temporary variable. Temporary variable now cannot be eliminated, cannot get rid of volatile reads and writes. And the last thing is an assignment of the static pointer. And since the last thing is a read from volatile, has to happen there, has to be last. Okay, we win. The victory will be very short-lived, unfortunately. The volatile keyword only applies to the C++ compiler. If you look at the object code, there is no volatile there. So now we have to think about what will the hardware do. And we know that basically if you read and write at the same time on multiple CPUs, this is in general not thread safe. There are all sorts of race conditions in hardware. But this is a talk about lock-free programming. Atomics have to be in here somewhere. So that's probably what's missing, right? We're missing atomics. Let's put them in. Okay, as I told you, I'm not using C++ 11, but you can map that atomic in this case by dropping the lowercase. So the static pointer will be atomic. Now, if you noticed volatile disappeared, there is an assumption that atomics have the volatile semantics. And if you look at how they're implemented, like for example, if you look at the GCC assembly, they do. We have atomics now. Since our main static pointer is atomic, we have to load it atomically, check for null. Then we take the lock. Within the lock, we can do a non-atomic load, it doesn't matter. And we have to do atomic store. Okay. Volatile, again, volatile semantics, there is no reorder. Oh. Sorry. Actually, yep. Okay. Sorry. Okay, so atomic has been introduced. There are volatile semantics. Compared to the previous slide with volatile, who thinks we fixed at least some of the race conditions here? And who thinks we haven't fixed any single one? Yeah, we didn't really fix anything. And this is probably the most teachable moment in this whole double-check locking pattern, so let's explore this. This is what we're counting on. Here is a... No, this wasn't what we're counting on. Okay, let me stick it in there. Can you hear me if it's lower like this? Okay. This lock is better. CPU issues some memory writes, and at first are the memory writes for the constructor, whatever we're using to initialize the object. And they happen first, and they get committed to memory first. Second is the memory write that commits the value of the address into the static pointer. And that gets committed to memory second. This is what we're counting on. This is not how the world works. And the reason this is not how the world works is because we have those pesky things called caches. And they're very annoying, they're very inconvenient, they make life very complicated. In the second half of the talk, you'll see why we still have them. So CPU indeed issues the writes in the order that I just described. There is no cheating here. First go the writes, first we write into the object, second we write into the pointer. That's true. What's not true is, not necessarily true, is what happens that those writes get committed to memory in the same order. What's entirely feasible, because at this point CPU has no control over what's going on. CPU finished its writing to cache, has gone on to do some other things. Cache gradually flushes it into memory, or maybe not gradually if you ask for it, but in any order it wants. In particular, it's entirely possible that in the main memory, the static pointer gets updated first. It's pointing to the location of the object, and what's in main memory at that location of the object, whatever was there before, random garbage. That's entirely possible. Now, this same CPU, if it starts reading, will read from its cache, so it'll see the correct picture. Another CPU that doesn't share the cache with this one will read from the main memory and will see incorrect picture. Okay, we won the battle with the compiler, we lost it to the hardware. Not good. Well, at this point, you should actually question, okay, if everything is so messed up, how do locks actually work?
A quick question.
Yeah.
Is that really true of C++11? Does the standard atomic stores that memory model sequentially existed?
Hold on to that question. There is more than one atomic. Actually, if you want to really know how many atomic stores there are, come to Michael Wong's talk. But I'll give you a simplified picture. There is a reason why I said atomic store. I'll say a little bit later about what kind of atomic store. Okay. Why does this never happen with locks? I have to introduce this concept of memory barriers. Michael will talk about memory barriers in great details, and specifically for C++11, 14, and so on. If you want to know, really know about memory barriers, also follow on with Paul McKinney's talk. But I'll introduce a simplified view of memory barriers. Without memory barriers, there is no concurrent programming, locks or no locks. Because memory barriers are what provides synchronization of memory visibility across different CPUs. Memory barriers are implemented in hardware. They are hardware specific. The last line used to be true. It's not true in C++11. There are portable memory barriers now. Okay. As I said, I'll give you a very simplified picture of memory barriers. There are two talks that deal with what's really there, if you really want to know how the world works. So I'll reduce the entire universe of memory barriers to two barriers, acquire and release. On x86, it's actually pretty much good enough for you to know. Not entirely, but close enough. Acquire barrier guarantees that all memory operations that were scheduled after the barrier become visible after the barrier. So whatever was in the program order after the barrier becomes visible after the barrier. Usually there is no acquire barrier per se. Acquire is a modifier on some other instructions like acquire read. Well, some CPUs have just a barrier instruction. So if this was the program order, then the memory visibility order could be something like this. You can go down through the acquire barrier, you just can't go up. Well, if there is acquire, there has to be a release. Release has the opposite guarantee. Anything that was done before has to be visible before the barrier. You can go up, you just can't go down. Okay, this is what locks do. Locks combine acquire barrier at the beginning and release barrier at the end to form what's called critical section. Anything that is done within the critical section cannot escape up or down. Any reads or writes that are done outside of critical section can enter critical section and be done there. But anything within critical section has to stay within critical section. So that's actually why the name is. You acquire the lock when you enter critical section, and you release the lock when you leave the critical section. That's why the barriers are called this way. Now, very important. When you use locks, it doesn't matter. When you start doing lock-free, people forget all the time. This gets you every time. Those memory barriers only work if both CPUs cooperate. It's not like a push across the entire system. Both CPUs have to take a barrier instruction. And then you get a synchronization between those. If one of the CPUs does the barrier and the other one doesn't, the second CPU can see whatever it wants in any order. No guarantees. It's a cooperative affair. Okay, well, Michael will actually cover this material in a lot more detail, so in the interest of time, I'll skip that. I just saw his slides, so I'm kind of adjusting some of the things. He'll cover it in a lot more accurately. Okay, let's before the break, which is coming up, let us finish this. So now this really works. This is a double check pattern that really works. There was a question about store, whether the store guarantees the store. Well, it has to be a release store. Now, on some platforms, every store is a release store, on some it isn't. But if, for whatever reason, by luck or by intent, your store is a release store, and of course the load has to be acquire load. Remember I said there has to be two memory barriers on both CPUs have to play. Then, yes, this is guaranteed to be executed in the proper order and become visible in the proper order. So what does it mean? Release store, all the writes that were done before release store have to become visible before so before you can read that value from whatever was release stored, all the previous writes have to be visible to you. And what are the previous writes? Well, that's the construction, initialization of the object. So all of those writes, which were done before we stored the address of the object into the static pointer, will become visible before you read from the static pointer, if you read with acquire load. So this double check pattern actually works. Atomic instructions, that's why I said atomic instructions are the easy part. 90% of all lock-free programming is about memory barriers and, in general, the visibility order.
So I asked a question.
Yeah?
I thought that, so I thought the lock created a critical section, and so therefore I thought we didn't have a problem without atomic in this case using the locks.
Lock creates critical section. Now,
So why, for example, why can't we just say static gives one pointer equals null, and then do the null check, lock, null check again, and assign without this atomic number at all? Why is that?
okay, look at the second line in the code. That line is outside of the lock, which means it happens before. Let's say that instead of acquire load, imagine that instead of acquire load, I said simply load, which is no barrier load. Now that line happens before the lock, which means no memory barriers have occurred on the CPU that is running this code. So now there are no guarantees on memory visibility. I can get a non-null pointer from that second line of the code, and the writes that were initializing the object may not be committed for another hour.
So this is like the previous slide, because now in essence you have one CPU that's not cooperating. He's checking memory that hasn't been synchronized.
Exactly. So we have two CPUs. The first one was really the first. So the first CPU went through and said, okay, is the value null? Yes, it is null, because it's the very first CPU. Let's do the lock. Okay, fine, we did the lock, we're the only one. Okay, let's check if it's still null. Yeah, it's still null, we're the first CPU going through. Construct the object, release store. Unlock. The second CPU is going through. Again, imagine that instead of acquire load, I say just plain load, no barrier load. Reads the null, gets non-null. I mean, reads the static pointer, gets not a null. Okay. Do I have any guarantees on the memory of the gizmo object itself? No, I don't. Those writes are sitting still in the cache, haven't propagated through main memory, haven't propagated back up, won't be propagated through main memory for the next hour. In reality, it doesn't live that long, but standard, you know, there is no guarantee. If you're not using barriers, there is no guarantee. I mean, on some hardware, it could be an hour. So those writes haven't propagated through the system to main memory. So if you didn't take the barrier, you will never go into the lock, which means you will never get any barriers at all, which means there is no reason for your main memory to be updated, ever. Remember, if you don't take barriers, memory updates are basically at the mercy of the hardware. Hardware may update them now, or next day, whatever. So if you don't have that first acquire barrier, you may run through this entire code and never hit a single memory barrier. Is that clear? No, second CPU sees that it's not null. Second CPU can see anything. If it sees that it's null, then it will try to initialize it again. Let's assume that it sees that it's not null. As I said, you know, any subset of the writes can be made visible, and the other subset non-visible. Let's consider the example where the static pointer was made visible and nothing else was made visible. Now the second CPU sees not null and reads uninitialized memory from the object itself, because no other writes have been made visible. Okay, let's, well, I think we actually have a, 30-minute break between the two talks, if I'm not mistaken, right? Sorry? Okay, so let me just go through all the way to the end, and I'll take questions between and for the second half. Okay, so as you saw, and we had just had a confirmation, lock-free program is mostly about memory order. Atomic instructions were the easy part. Yeah, atomic read, atomic write. Every shared variable that you read and write without the lock has to be atomic. That's easy. You have to take the correct memory barriers and order your code correctly between those memory barriers to make sure that what you think is done and should be visible is really visible. Now, this whole thing went away with C++11. If you have C++11 and you want static singleton, you do this. And this, according to standard, is thread safe and is guaranteed to work. What the compiler do is very much what I just shown you. You can look at the assembly, that's something very similar. Now, the reason I'm still talking about it, one, it's relatively easy to explain. It's not very easy, but it's probably the easiest vehicle I have for explaining the memory dependency issues. But more importantly, while in like pretty much every talk on double-check-locking pattern uses that singleton initialization, that's not the general pattern that it's solving. Think for a moment, what's the real problem that we're solving? We have normal case, which always happens, and exceptional case, which rarely happens. when exception case actually happens, it's difficult to handle. There is a lot of data to be messed with, so in general you want to have a lock protecting it. It's not thread safe, it's hard to make thread safe, but you don't want to take that lock every time. The problem is, in order to test, you have to test for the special case and handle special case in an atomic transaction as a single non-interruptible operation, which means the only way to do it with a lock is to put a lock around both the test and the handler of the special case. 99.9% of the time, the handler doesn't need to run. In case of Singleton, like almost never, the handler doesn't need to run. But the test is still guarded by the lock. That's what we're trying to solve. That's what we're trying to avoid. Now, when can we use double check locking pattern? Let's assume that we have a very fast, non-locking test for whether we are in trouble, whether we need the exceptional handling. And I don't mean C++ exceptions, I mean just something that is not usual. There is no false success. If the test says we're good, we're good. If the test says no, we may be in an exceptional situation, we may or may not be in an exceptional situation. This is the case with that singleton. If the pointer is non-null, assuming you have written it correctly, if the pointer is non-null, go ahead and use the object. If the pointer is null, maybe the object needs to be created, maybe it isn't. Maybe somebody is creating it right now, in which case you shouldn't be. So this is the double check locking pattern. This is the case where it's used in general. When you want to test for a special case very quickly, a lot of times, without a lock, and if the test for special case shows you that you may be in an exceptional situation, then you take the lock and really figure out where you are. In case of Singleton, once the test succeeded, it always stays succeeded. In general case, that doesn't have to be true. Double check locking pattern actually doesn't depend on it. You could go into, like, basically, if you handled your problem, you may have to handle it again later, just not very soon. Okay. You will see why this is actually very useful in practice. So this is kind of the pseudocode for the general double check locking pattern. If the fast test fails, we have to lock, we have to do the exact test, we have to handle the problem, and we have to unlock. Now, there is another assumption here. The assumption is that basically, if the problem happens after if one thread goes through, does the fast test, and the fast test succeeded, you can actually keep using whatever you were, whatever, like your object or whatever it is you were trying to use, even if the problem later happens. So classic example is memory allocation. If you're testing for whether I have all my memory allocated. If you do, that memory is not going away. You already got it. If the memory allocation fails, you run out of memory. Whatever you allocated is still there. You may not be able to allocate new one. You have to handle it. But the idea is basically if the fast test passed, then you're good. Nothing that happens afterward can break your well-defined behavior. This will come very useful later during the second half. Okay, good time to take a break. If you have any questions, come see me. Otherwise, we'll resume for the second half where we change gears and look at some real lock-free programs. Start with some queues.